So this is podcast topic 3, lesson 2. It will be on the basics of the structure of an atom, as well as isotopes and a little bit about ions and how to calculate isotopes. So what you'll want to do is you'll want to write down this chart about subatomic particles. It's going to summarize everything all the basics you need to know about protons, neutrons, and electrons, which are subatomic particles. Subatomic, sub meaning below or smaller than, and atomic meaning obviously atomic, so smaller than an atom. Particles would be the protons, neutrons, and electrons. And so first of all, let's go ahead and talk about the charge on each of them. So the proton's charge is positive. If you're pro something, you're for it, so positive. Neutrons are neutral, so they don't really have a charge, and electrons are negative. Where they are located, we talked about a little bit in our previous podcast when we were talking about the discovery of, like with Rutherford's gold foil experiment and Thomson's cathode ray tube experiment. So protons are located in the nucleus, neutrons are located in the nucleus, but electrons are located on the outside of nucleus. And I want to talk about that in a little bit more specifics. So we know, and you're familiar with Bohr's model, and if this is the nucleus, then you have a first energy level, second energy level, so on and so forth. And according to Bohr's model, these two electrons that are in the first energy level would be on the actual orbital, and they would orbit around. Well, we know that not to be true at this point with our modern atomic theory or wave mechanical model, which indicates that these two electrons are not in a line orbiting around, but they're kind of in this area of the first energy level. And I like to do an analogy of recess and having the students be representing of the electrons. If there was recess for kindergartners, first graders, and second graders, the kindergartners probably could only go this far from the door. First graders this far, and second graders maybe this far. Oops. And so when they're out, the two kindergartners are not just going to stay on this line and go back and forth, they're actually going to play within this given area. Same thing with the first graders. The first graders are not going to just stay in a line, they're going to go within this given area, and it's going to be actually a little bit bigger than the kindergartners area. And so on and so forth. As you get older in your levels and have more responsibility, you can go further from the nucleus or further from the school, further from your teachers that are pulling you in. So let's just say Johnny's in second grade and he got called to the office and I'm Johnny's teacher. Not only am I going to know that Johnny's going to be in this area, but I know Johnny a little bit more, and I know that Johnny really likes to play on the monkey bars. The monkey bars are in this area, the basketball courts are here, the slides are here. Well, Johnny likes to be in the monkey bar area, so I'm going to look right over here because that's the area where he is most likely to be found. Within these levels, there are areas that electrons are more likely to be found. Some are going to be found in the monkey bars, some are going to be on the slides, some are going to be on the basketball courts, but an area where an electron is most likely to be found is called an orbital. Now, I don't want you to get that confused with orbiting. They don't orbit. They're within an energy level in a given area. Is Johnny always on the monkey bars? No, but 90% of the time he is, so that's where he's most likely to be found. Okay. Excuse me. Going on to mass. Now, what we're going to do is we're going to see whether, this over here. Each of these subatomic particles have mass, and we did discover this a little bit in our gold foil experiment with Thomas when we were talking about Rutherford. Protons do have mass, neutrons do have mass, but electrons do not. Technically they do, but it's so negligible, it's so teeny tiny, it's like 1,800 and some odd number that you'll have to have of electrons to make up one proton that we don't even count it into its mass. So we know that protons and neutrons are the only ones that have mass, and just as a review, remember we said that the nucleus is extremely, 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 extremely tiny, but it's very, very, very dense because that's where all the mass is. So a very small volume, but all the mass makes up a very dense part. And so the neutrons and protons make up the mass, and they are located in the nucleus, where is where all the mass is. How to calculate protons? Well, that's actually pretty simple. I'll go to the next slide here for a second. The number of protons is the atomic number. And so because of that, like when I bring this periodic table up, it's always the same. I never have a different, like carbon is never found at number 29, and it's never moved around. This is where they're located. And because they're located according to their atomic number, and the atomic number is also the number of protons, the number of protons never ever changes. If I have 28 protons, I'm nickel. Done. There's no arguing of it. If I'm oxygen, I have 8 protons. That's all there is to it. So the atomic number is the number of protons. Never changes. So it's always atomic number. It's always the atomic number. All right. Now on to neutrons. Neutrons is a little more involved, but not very much. And so if we take a look at what we already know, in the nucleus we have our protons and neutrons. And in the nucleus is where our mass is. If I go back to the periodic table, and let's just take fluorine, for example. Fluorine has a mass of 19, if I round it up, an atomic number of 9. Oops. So if we have fluorine, which has a mass of 19 and an atomic number of 9, we know that the number of protons is going to be 9 because it's an atomic number. The number of neutrons is what we're trying to find out. Well, the mass we know is 19. And if the number of protons is 9, and the only other thing that makes up the mass is the neutrons, how much is left? 19 minus 9 is 10. Protons plus the neutrons gives you the mass. So if you know the mass and you know the atom, you know the atomic number, you know the number of protons, you're good to go. So number of neutrons is the mass minus protons, which is your atomic number. So now let's take a look at our electrons. So how many electrons are we going to have here? Excuse me. Number of electrons varies. If it's neutral, meaning pluses and minuses are the same. Well, if I have 9 pluses, how many minuses am I going to have? I'm going to have 9 to come out with a neutral charge. So for a neutral atom, the number of electrons equals the number of protons. But there are some instances where the atom is not neutral, and that's where we're going to be going to next, or in just a minute. So let's go on to our next slide here. When subatomic particles numbers change, but the element type does not. Well, first of all, protons, neutrons, electrons are subatomic particles, and protons cannot change. So we're talking about when neutrons and electrons change. So isotopes is that when neutrons change or when electron number changes. Well, isotope is another way of saying type of atom. So if I go back and I look at carbon, for example, there are multiple types of carbon. Let's just say there's carbon 12, there's carbon 13, and carbon 14, which means there's carbon that has 6 protons but has a mass of 12. There's carbon that has 6 protons but it has a mass of 13. And there's carbon that has 6 protons but it has a mass of 14. Well, since we know that the protons and the neutrons are what make up our mass, and if the protons aren't changing, what do we know must be changing? It must be our neutrons. So, isotope is a type of atom, or types of atoms, types of same element. And how they differ in neutron number because they differ in their mass. In class, I'll talk about carbon-14 and carbon dating and other isotopes, natural and radioisotopes. But what you need to know about isotopes is that they are the same element. Their proton number never changes, but their mass does. So that means their neutron number is changing. So what I want to do is I want to show you how we calculate atomic mass. Let me just go back real quick again to this periodic table. We said that the mass is made of protons and neutrons. But if we look at the mass of carbon up here, it's a mass of 12.011, which doesn't really make sense if the number of protons is a whole number and the number of neutrons is a whole number. Then the protons plus the neutrons should be a whole number. But it's not. And why is that? That's because when they take the mass, they're taking the weighted average of the naturally occurring isotopes. In other words, we have carbon-12, carbon-13, and carbon-14 in a sample. So I know that most of that sample is going to be carbon-12 because the atomic mass of carbon is closest to 12, but there's going to be some carbon-13 in there and some carbon-14 because the average atomic mass is a little bit more than 12. So let's go ahead and calculate, or how do they calculate that atomic mass? I'm going to show you how, and we're going to be doing a lab which will reinforce this as well as a lot of other examples. So don't worry if you don't have it 100% down, but please make sure you take notes, you pause, you rewind, and then you ask questions in class while you're applying this information if you don't get it. Okay, so here we go. We have isotope of element X are X17, X16, and X15, which means X's mass can be 17, 16, or 15. And let's just say X17 is 36%, X16 is 52%, or sorry, 16 is 52%, and X15 is 12%. Well, just looking at this, and you always should predict before you go ahead and do the math, most of my element X has a mass of 16, so my answer should be closest to 16. But the fact that I have more of X17 than I do of X15, it should be closest to 16, but a little bit larger because I have more 17 than I have 15, so it should be a little bit larger than 16. So let's see if we can calculate this and excuse me, come out with the right answer. All right, so the first step that you do is you take, and if you want to write down these steps in words, you should do so in your notes. You want to take the percentage of each of the isotopes and put it in a decimal form. So I'm going to take 0.36, 0.52, and 0.12. And then what I'm going to do is I'm going to multiply their percentage by their mass. So element 17, mass 17, there's 36% was mass 17, 52% was mass 16, and 12% was mass 15. This is how they do your weighted averages, by the way. For instance, test quizzes, homeworks, labs, like if they say 50% is tests and 30% is this and 30% is that, that's what you would do here, is you take your percentage and you multiply it by your average for your tests, your quizzes, and whatnot to get your overall average. So anyways, you take your percent, you multiply it by the mass, that is that percent, and then you would get how much each mass contributes to the overall atomic mass. So for the first one, 0.36 times 17, if I do that on my calculator quick, I get a contribution of 6.12 grams. And 0.52 times 16 is 8.32 grams, which makes sense. Even though it's a less mass, I have a higher percentage of it, so I should have most of my mass being contributed by element X16. And then if I take element 15 and I multiply it by 0.12, or it's 12%, I get 1.8. So now that I have all of the isotopes' contributions to the mass, I can now add them up and calculate that the average atomic mass of this element is 16.24. Now, does that make sense according to what I said? It would be closest to 16, but a little bit more, because more of it is 17 than 15. And it does. So that's how you would do a calculation of average atomic mass. So, going back to our chart, I want to put in here the neutrons. They can change. And when you have the same element, but they have a different mass, they are called isotopes of each other. All right, now what about this thing called an ion? All right, well, ions is the other thing. Remember, we said protons can't change. If neutrons change, they're isotopes. So now we're left with electrons. Well, ions are charged particles. So, it's a charged particle. Protons have a charge, but protons can't change. Neutrons don't have a charge, so that isn't going to make an ion. Electrons have a charge. So, in order to make a charged particle, you have to be either gaining. Let me erase that. You either need to gain or lose electrons. So, for instance, let's go back to, well, let's just do potassium here. Potassium has a mass of 39 and an atomic number of 19, so let's do that. So potassium, 39, and 19. Now normally the number of protons would be 19. Neutrons is going to be 20. So you have to subtract. Number of electrons is going to be 19. Neutral, right? But if I have something like this, okay, 39, 19, but it has a +1 charge, Protons never change, so they'll be 19. Just because it has a charge doesn't mean neutrons are going to change, because neutrons don't have a charge. So my electron number is going to be different. Well, if I have to come up with a +1 charge, this is a 0, if I have to come up with a +1 charge and 19 are pluses, then I better only have 18 minuses to have a +1 charge. So because I have a +1 charge, I'm called an ion. I'm called an ion. And because I have a +1 charge, that means I have one less electron than I normally would have. Now let's just take, and I'm going to erase this entire, well, no, erase the entire slide. I'll just erase what's over here. Okay, so let's just take fluorine again, for example. And fluorine was 19 and 9. So normally the number of protons is going to be 9, the number of neutrons is going to be 10, and the number of electrons is going to be 9. But when fluorine becomes an ion, it becomes a -1 charge. Excuse me. Protons don't change. Neutrons will be 10. But the electron number, oops, since I have 9 protons and I have to come out with a -1, I better have 10 negatives. So when you have a negative ion, you're gaining electrons. When you have a positive ion, you are losing electrons. All right, so let's go back here. Protons, they never change. Neutrons, they can change, and if they are, they're an isotope, and what's changing is their neutron, the neutron number, which is changing the mass. And if electrons, they can change. If they change, can change. If they change, it's called an ion. And I'm going to put this over here. Positive ion equals a loss of electrons. Negative ion equals a gain of electrons. So a positive ion is a loss of electrons, and a negative ion is a gain of electrons. And I think we're all set, and we've gone through the entire podcast. So hopefully that helps with a summary of our subatomic particles.